Welcome to this Dutch mini lecture. My name is Baoqiang Ma, and I'm a PhD candidate at the University Medical Center Groningen, working on artificial intelligence applications in radiotherapy, with a focus on head and neck cancer. In this mini lecture, I will talk about HECTOR 2021 challenge on head and neck tumor segmentation and outcome prediction in PET-CT images, and how my team and I approached the task of the prediction of progression-free survival using deep learning-based methods. HECTOR 2021 is a challenge on automatic head and neck tumor segmentation and outcome prediction in FDG-PET and CT images. The tasks proposed were three. Task 1 is about the automatic segmentation of head and neck primary tumor in PET-CT images. Task 2 and Task 3 are about the prediction of patient outcomes, namely progression-free survival, from the PET-CT images and the available clinical data, with or without using the ground truth delineations of the primary tumors. This lecture will focus on Task 2 and 3. Let's give some background information about this topic. Head and neck cancer is a very common cancer, and the long-term survival of it is quite poor. In clinical, radiotherapy is a primary way to treat head and neck cancer. An outcome prediction model can help identifying high or low-risk patients prior to the treatment. Then more specific treatment plan can be made for patients. For example, high-risk patients could be assigned to a more intensive radiation dose for outcome improvement, and low-risk patients could receive a more moderate treatment to alleviate side effects such as xerostomia. The outcome endpoint in this challenge is progression-free survival. The PFS is the time after treatment to the tumor progression, which includes three endpoints: tumor size increase, tumor recurrence, and disease-specific death. The dataset consists of 325 patients from a total of 6 centers, 4 from Canada, 1 from France, and 1 from Switzerland. The training set includes 224 patients from 5 centers, and the testing set for final ranking includes 101 patients from 2 centers. Only 1 center of the training site is also present in the test site. 3D CT PET and GTV contour of primary tumor images are available for each patient in the training site. For testing site, GTV contour is only available when the challenge organizer run our submitted Docker command for C-index evaluation on the test site. CT provides information about the anatomy. PET provides information about the metabolic activity of the tumor. For consistency, the GTVT for these patients were delineated by experts following the same procedure. The age, gender, T-stage, N-stage, TNM group, HPV status are available clinical data for each patient in both training and testing sites. To use clinical data as potential predictor for PFS, we normalize the age by dividing it by 100 and use other clinical data as category variables. To use image features from CT PET and GTVT, we also need to do pre-processing for them. Firstly, automatically generated bounding boxes provided by the challenge are applied to crop 3 cubes around the oropharyngeal cavity from CT PET and GTVT of each patient. Then each cube image is reassembled to 1 cubic millimeter isotropic resolution with a size of 144 pixels. Secondly, CT and PET images are normalized and then combined to obtain a combined CT-PET image by summing up their intensity values. Finally, we crop the tumor images by multiplying GTVT with CT, PET, or combined CT-PET, and then crop the multiplied images by the size of 2, 6, 4, 6, 4, 6, 4. The whole method includes 3 steps. It was first mentioning that we use 6-fold cross-validation, in which 5 folds are obtained by leave one center out method, and another fold is from random selecting some patients from the training site as validation site. First step is deep learning-based identification of image features. 3D pyramid autoencoders are applied to extract the features from CT PET and combined CT PET in both task 2 and 3. Because GTV contours are only available in task 3, image features can also be obtained from CT PET combined CT PET tumor images. In the second step, feed-forward selection method is used to select useful features for PFS prediction from image features and clinical parameters together. The last step is for building PFS prediction model using selected features. Deep survival model is used here as a deep learning-based survival analysis method. For each fold, 30 deep survival models are built using same selected features, but finally, only 3 best models with highest validation index are saved. 18 best models are saved from 6 folds in total. Finally, all models outputs on test site are average assembled to obtain the final PFS prediction on the test site. The pyramid autoencoder used for image feature extraction consists of an encoder and a decoder. Encoder compresses input image to deep image features. Decoder reconstructs the input image from deep image features. And an additional pyramid architecture is used to combine different level image features. The loss function is applied to check the similarity between the input and the reconstructed images. It consists of L1 loss, mean square error, and structural similarity. At the last layer of encoder, an average pooling layer is used to decrease the size of feature maps to obtain 512 and 32 image features in task 2 and task 3 respectively. After getting extracted image features from autoencoders, we select features relating to PFS prediction. Feature selection is performed using training set data. Firstly, we randomly select n samples from training site. Secondly, we perform forward feature selection by Cox model. Those features with p-value less than 0.005 in build Cox model are selected. We run the forward selection 1,000 times in total. Finally, we rank all features by their total selected frequency in 1,000 times. The features with high rankings are selected for building PFS prediction models in the next step. Deep survival is a deep learning-based survival analysis method. In this work, its input are selected features and the output is the risk score of each patient. Negative log likelihood is used to train the model. From the hazard function of deep survival model, we can see the deep survival uses neural networks to nonlinearly combine the impact of corollaries, which are the selected features in this work. However, Cox model can only do a simple linear combination of the impact of corollaries. If the deep survival network has only one input layer and output layer. It can only perform linear combination too, just be similar to a Cox model. The reason why we choose deep survival is for finding more complex associations among the impact of covariates to PFS prediction by nonlinear combination. The figure shows the input and output images of pyramid autoencoders. By the comparison of the input images in the first row and the output images in the second row, we find that the tumor images and shapes are successfully reconstructed from deep image features in the output PET combined CT PET images, and also in CT PET combined CT PET GTV tumor images. So, we think that the extracted image features by autoencoders can stand for the tumor information well. In the first table, we summarized the C-index values on the training side and the validation side of the best deep survival models, which have highest validation C-index of all fours in taxa 2 and 3. It's easy to notice that the C-index values on all validation sites are pretty high. The C-index values on the taxa sites is displayed in the second table. Although the C-index values on the taxa sites are not as high as that on the validation sites, we still obtain good C-index values of 0.6445 and 0.6373 in taxa 2 and 3 respectively. In conclusion, the aim of this work is to build a progression-free survival prediction model for head and neck cancer patients using CT, PET, and GTV contour of primary tumors. The proposed method, which uses self-learning for image feature extraction and deep survival for PFS prediction, achieves good performance in both taxa 2 and 3. In the future work, 3 aspects of this work can be optimized. Firstly, improve the C-index on the training site. We found that the C-index values on the training sites of some folds are lower than 0.6, so they probably can't give a good PFS prediction on the taxa site. We should make the deep survival models have both high C-index values on the training and validation site in the future. Secondly, use different splitting method of the training and validation site, not leave one center out. When we use leave one center out cross-validation, some centers has too less patients, which makes them not suitable for validation site. Finally, because the limited number of 224 patients in the training site, we use the same patients as the training site for autoencoder and deep survival, which will make a deep survival model overfit on the training site. In the future, if we obtain more patients' data, we could use different training sites for autoencoder and deep survival to avoid the overfitting problem. This is the end of the lecture. I'm glad to have this opportunity to share my team's work. Thank you for your attention.